In this video, we're going to be talking about random processes, and so with that, we'll go ahead and begin. Just a quick review, sample space is just the set of all possible outcomes. So for flipping a coin, we've got a sample space of heads or tails, and rolling a die, we've got 1, 2, 3, 4, 5, 6. We could have something like the cycle time for a CNC machine, and that could range anywhere between 1.25 and 1.28 minutes. So all of these are example sample spaces. Now, we can have some definitions, of course. There are two classifications for random processes, and that's depending on the structure of the sample space. And this is really pretty obvious stuff. So we can have something like a discrete random process, and that's got a discrete sample space. So producing cars would be a discrete random process, and the number of cars you could produce would be the discrete samples or within that particular sample space. Now, this is opposed to continuous, and I can spell that because it is right here for continuous sample space. So an example of that might be something like the jet fuel used on a flight. I mean, if you really wanted to get super picky, maybe there'd be the molecules, and that would be discrete, but we're not going to be that picky, so we'll just say that jet fuel is actually a continuous sample space. So we can say that we can give a definition, and that definition would say that two outcomes from the same sample space are mutually exclusive. That means they're rather snobby, right? If the intersection of those two outcomes is the null set. Mutually exclusive means that two events can't occur at the same time. So if you roll a 1 with a die, you can't roll a 2 with a die. That holds for however many, like for a die, there's 6 sides on the die. They're all mutually exclusive, and that means that the intersection of one with another event is the null set. So as an example then, you could flip a coin, and you could get either a head or a tail. Well, then you know that each event is actually mutually exclusive. Likewise, if you roll a die, you can get 1, 2, 3, 4, 5, 6. But if you selected one event would be odd numbers and the other event would be a number less than 3, then, as it turns out, E1 and E2, these two different examples, are not mutually exclusive. So each one of these events, I should say. So then we can say that if we consider a discrete sample space, and that discrete sample space is S, every single elementary event satisfies the following conditions. It has only one element, and they're all mutually exclusive. So you can see that the 6 different faces on a conventional die they satisfy these properties, and so those would be considered elementary events. Now let's say that we roll a die, and we've got the following sets, which are elementary events, and then these sets, as it turns out, are not elemental events. So we've got odd number, and that's 1, 3, or 5, or a number greater than 4, so that's 5 or 6. So these events aren't elemental. And this isn't magic. It's just we're going to see that this conceptualizing things as an elemental event as opposed to a non-elemental event will help us when we're solving probability problems. So we just need to make it clear here what is an elemental event and what is not. Then we can say elemental events satisfy these properties. Any event such that the event is a subset of the sample set can be described in terms of the union of a bunch of those elemental events. We could say the event of whatever can be unioned together. Each of the elemental events can be unioned together to describe that event. If you've got n of those elements, there are elemental events, for example, 6 faces on a die, then the sample set is just the union of all of those elemental events. For example, let's roll a die, and we know the sample set is 1 through 6. If our event is an even number, then we can say that the event is 2 unioned with the elemental event 4, and likewise unioned with 6. And so that is 2, 4, or 6. Also, we can say that the sample set itself is the union of all of these different events. So, the frequency definition of probability, if we have a random process and we've got an event that's a subset of the sample set, and we repeat a random process n times. For example, we might roll a coin 15 times. We could let NA represent the number of times that A occurred. For example, maybe that we got heads. Then the probability of A, in other words, getting a head, would be given by the number of heads we actually rolled divided by the number of times we rolled. And we let that number of times go to infinity. So we note that this P of whatever is called a probability function. It's okay to use that as a mathematical definition, but we really have a little trouble using it in the real world. So let's flip a coin, and let's let A be that it is a head. What's the value, the probability of A? We know it's got to be 0.5. When we actually collect data, we may get something a little different than that. If we roll the coin 10 times, we may get 0.4 as our chance of actually rolling a head. Do it 100 times, 56. 1,000 times. You can see that the more we roll, the closer we get to 0.5. And that's what we expect from looking at the probability theorem. So, as far as definitions and properties go, we can say that, well, first of all, the domain of a probability function is the sample space. On the other hand, the range of a probability function is the interval from 0 to 1. That is, for any event A, it goes between 0 and 1. You say, what's the probability that will roll ahead? Well, it's 0.5. What's the probability it will rain tomorrow? Well, maybe 85%. But notice that's 0.85 actually. You can't have that the probability that it's going to rain tomorrow is 115%. It's just not, it doesn't work that way. All of this is valid even if that particular event is not within the sample space, because in that case you can say that the probability of that event occurring is just 0. Now, as far as axioms of probability go, for any event A, we can say 0 is less than or equal than the probability of A is less than or equal to 1. Now, if A is equal to the sample set, that event is actually equal to it, then you can say the probability of A has got to be 1. And if the events A and B are mutually exclusive, right? So in other words, the intersection of them is the null set, then you can say that the probability of A union B is equal to the probability of A plus the probability of B. Now later what we're going to see is this. If they're mutually exclusive and we have A intersect B, then you're going to have this relationship. You can multiply the two probabilities together. So these are very important findings, and we will be using those all the time. Now let's have a little bit of an extension on this axiom. If we have a bunch of events and they're all mutually exclusive, then, well, obviously, we would just sum them all together. So if we wanted to know the probability that we would have a bunch of events, like I would roll a 1 and roll a 2 and roll a 3 all the way to 6 on a die, then we could sum up all those probabilities. If I had 1 through 6, it would be 1 6 plus 1 6 plus 1 6 and so forth all the way, and we'd have a total probability of 1 for that whole probability space there. So we can note then that if you union all these different events all the way through n, you can just write it in this fashion. Now let's take our first random process here. We can say that if we have a random process which satisfies the following conditions. The random process is discrete. It does not mean that it's coy, but it is a discrete random process, comes in chunks. The discrete random process has a finite sample space, and it contains n elemental events. All the elemental events are equally likely to occur. Now this sounds suspiciously like rolling a die, right? We've got all the elemental events, which is each of the different faces of the die that could turn up. Then the probability that any of those events will occur is actually 1 over n. So look, for a die, we know n is equal to 6, so the probability of each one of those elemental events occurring is going to be 1 over 6. And we can prove it by saying that if we have n elemental events, the probability of that entire sample space occurring is just the union of each elemental event, and that probability of the union of all of these, which is just 1. And then we can say the probability of, we can rewrite that probability as separate additions, because each one of those elemental events are actually mutually exclusive. And thus we can say, well, we know that each one of those elemental events will sum to 1. In other words, we had n elemental events, n times the probability of each of those elemental events should all sum to 1. We can rearrange this, and there we go. We've got our proof that the probability of each elemental event occurring is just 1 over n. Now let's take an example. Let's say we toss a die, and we know what our sample set is there. If we want to calculate the probability of the elemental event 2, where that is, well, 2, then we can say that the probability of the elemental event 2 occurring is just 1 over n, which is 6. Okay, now what we want to do is we want to calculate the probability of the event where that event consists of us rolling a 1, a 3, or a 5. So to do that, we can say that probability of the event where we've got a 1 union with a 3 union with a 5. Well, if you look at that, remember, whenever we're unioning, that means we can add the probabilities. So we can say it's the same as the probability of throwing a 1 plus probability of rolling a 3 plus probability of rolling a 5, which is 1 6 plus 1 6 plus 1 6. And all of that together is 0.5. So, oops, there's a point. So there we go. That's really not too hard to do. Now let's look at a counting problem. If we want to consider a discrete random process where we've got the sample space has n elemental events, and each elemental event is equally likely to occur, then for any event E that's a subset of that sample event, we can write that in this fashion. We can say the probability of that event is the number of ways that E can occur divided by n. And then we note that the number of ways that E can occur is actually equal to the number of elemental events within that set. Now notice this, because we're gonna play with this a little later, and this is actually going to be the solution to a conundrum that I will pose to you. So, okay, this is your comic relief here. Here we go. This is things I learned from watching CSI. Actually, I like to read the National Enquirer, but we won't go there. So we'll say we learned a little bit about how to take fingerprint samples and which way blood spatters. But my favorite of all is that you can kill someone with just about anything, which is probably sadly true. So anyway, okay, so enough of that. Off we go to the next one. What is the probability of selecting an ace from a deck of cards? Well, we could have an event which is that we're going to select an ace. And we can say that we've got 52 cards. That's our n. That's the total number of cards, and all outcomes are equally likely to occur. Now the number of ways we can pull an ace, well, there's 4 of those, right? So we can say, using that previous equation, the probability of that event of selecting an ace is going to be the number of ways E can occur, which is 4, over n, which is 52. And there we go. That's what, if you're particular, it's 0.077. Now let's see what happens if we roll 2 dice and we let the event be the sum of the dice. Now this is a little bit different than what we've been doing before, so I just want to stop and look at that for a minute. It's going to be the sum of the dice. So if we roll 2 dice and we have a 1 and a 1, right, then what we're going to have is 2. So that's actually the lowest that we could get, because you can't have a 0 on any of the dice. You can have a 5 on each dice, or on each die. That would sum to 10. But you could actually also get it if you didn't do it that way. You could say, well, I rolled a 4 and a 6. 2, 3, 4, 5, 6. Okay, so you could, there's several ways to get at this. So if we look at our sample space, we kind of have to understand what that sample space actually is to get a grip on how to calculate these odds. So let's first take a look at this sample space. If we have a 2, remember I showed you before, we can roll that just one way, right? 1, 1. 3, we can roll a 2 on this one and a 1 on this one. Well, let's take 6. Well, we could roll that as a 5 and a 1, or a 3 and a 3. There's a lot of different ways we could roll this. So in other words, not all the outcomes are equally likely to occur. Now that was a key factor that we were noticing before. So let's look at this sample space. Does this get us where we need to go? Well, we can roll 1, 1, 1, 2. Yeah, we can roll 1, 2, but what if we rolled a 2 and a 1? Clearly this material here, it doesn't give us all the ways. Like this gives us 3 different ways of rolling a 7, but there's actually 3 more down here. So in other words, not all outcomes are equally likely to occur, even with this configuration. So we go to this sample space. This is the one. Since there's only one way to roll every elemental event in here, each elemental event is equally likely to occur. Yay! We found it. Okay, so now that we've got that, let's go and look back. What's the difference between those 2 sample spaces? Well, I already talked about it. It's order matters. And that's why you need this complete sample space here, which has all of the elemental events within that sample space. So if we look at this, remember we were trying to figure out what's the probability of rolling a 2. Rolling a 2, there's only one way to do it. So it's 1 out of 36. Rolling a 7, let's see, we got 1, 2, 3, 4, 5, 6. So it's actually going to be 6 out of 36. And that's our probability for rolling it. So it's just important to get down to elemental to see what's going on with the elemental events if you're going to calculate probabilities. So note that the probability of an event A occurring is going to be, if that probability is 0, that means that event cannot occur as an output of the process, which usually means it's not a subset of that sample space. Now likewise, if we have that the probability of that event is 100%, then that means the event must occur as an output of the process, and it's not random anymore, it's deterministic. If the probability of a null set occurring is 0, and that means that the probability that a random process has no outcome whatsoever is 0. Now let's look at the properties of the probability function, and you're going to see that this is sort of a back-ass words, as they say, a way of approaching probability when it's sometimes easier to calculate the probability of an event not occurring than it actually occurs. You can say that the probability of some event occurring is actually equal to 1 minus the probability of its complement occurring. So, easiest way, we're engineers, we like to have a concrete example, and so for that we can say, what's the probability of not rolling a 2 with a single die? Well, the easiest way to calculate that is to say is to go like this. The probability that you're going to have not 2 is going to be 1 minus the probability of 2. Well, that's just 1 minus 1/6, which is 5/6, and so there you go. That's the easy way of calculating that one. So now let's look at some fun ones. This is find the errors in each of the following statements. And if you want, you can just pause this and see if you can figure it out before I'll tell you what the errors are. Okay, so you're back from your pause, I hope. And the probability that it will rain tomorrow is 0.4, and the probability that it will not rain tomorrow is 0.52. Well, the problem there is it doesn't sum to 100%, so that just won't work as a probability. Let's see, the probabilities that a printer will make 0, 1, 2, 3, or 4 mistakes in setting a document are, well, you can see what's going on here. We've got a negative probability, which I would love to have that happen in the real world, but we just don't have it right now. So that's the problem with this one. Now, on a single draw from a deck of playing cards, the probability of selecting a heart is 1 out of 4. Probability of selecting a black card is 1 out of 2. Okay, that makes sense. And the probability of selecting both a heart and a black card is 1/8. What's wrong with that picture? The probability that you could get both a heart and a black card is 0. So that just doesn't work. So now let's look at how we can calculate and in relation to probabilities. And we actually covered this just a little bit already. So remember that if both events occur, or A and B occur on a single performance of an experiment, that's called the intersection or joint probability, and so that would be PA intersects B, and we denote it like that. And then we can say the probability, if those two little rascals are independent from one another, That means the one doesn't affect the other. That's different than mutually exclusive. Independent means that if I roll a head this time, then it doesn't affect my ability to roll either a head or a tail the next time. Mutually exclusive, however, means if I roll a head, I can't roll a tail because it's already sort of taken up that space. So that's the difference between independence as opposed to mutual exclusivity. But anyway, so this is what you want to note down, which is the probability that A intersect B. If those two are independent, then you can always calculate the probability, the joint probability, by simply multiplying those two probabilities together. Again, that's only if they're independent. And so sometimes what you'll see, like on tests, when I give you problems, you'll see that, oh, if you just remember this relationship, it's easy. Now, you may find out that they're not quite independent, and I'll teach you how to handle that pretty quick. If we have or in relation to probabilities, we can say that if either event A or event B, or both events, occur in a single performance of the experiment, that's called the union of the events A and B. So we can say it's A union B. Remember, that's also, we can call that or if we want, because there's the little or coming off of there. Okay, so if those two events are mutually exclusive, then the probability of either one occurring, probability of A union B, is, well, probability of A or B, if we want to rewrite it that way. And we can calculate that by adding those two probabilities together. And again, that's only if they're mutually exclusive. Well, let me give you one example. The chance of us rolling a 1 or a 2 on a 6-sided die is, for, we can say, the probability of, oops, that's a die, not die, you know what I mean. Okay, so probability of 1 or 2 is going to be probability of 1 plus the probability of 2, and that's going to be 1/6 plus 1/6, and that's equal to 1/3. Okay, got that. Now we're going to go on to figuring out the sneaky case when A and B are not mutually exclusive. So one would, if that turns out to be the case, if probability of A union with B is not mutually exclusive. Now, when could that be? That could be something like this. Here's A. You got your A. You got your B. Okay. Now, oh, wait a minute. We got this overlap here. So they're not mutually exclusive. That's the kind of problem I'm talking about right now. So if it's not mutually exclusive, we can calculate the probabilities by adding probability of A, probability of B, and subtracting the probability of A intersecting B. Why? Because if you take this whole thing, that's probability of A. Your probability of A, you're counting this little part. Probability of B, you're also counting that little part. So you're double counting the intersection. So you got to get rid of it. So you subtract it off. So now the probability, well, so note this is equivalent. If A and B are mutually exclusive, that means you got your A here, you got your B here, and never the two shall meet. Well, then this intersection is automatically 0. So it just devolves to the previous calculation if they are mutually exclusive. So now what's the probability of rolling a 2 or rolling an even number with one die? We can say, if we want to calculate that, we can say probability of 2 or even number. Well, let's see, that's probability of 2 plus the probability of an even number, and then we're going to actually subtract the probability, oops, ignore that, probability of 2 and even number, right? Because that's where they overlap. So we can say the probability of rolling a 2 is 1/6. Probability of rolling an even number is going to be 1/2. Probability of us rolling a 2 and an even number is 1/6. So we end up with that probability as being 1/2, as it should be. So next, we can say that if we have an application where we're drawing a single card at random from a regular deck of cards, what's the chance of getting a heart or a face card, or one that is both? Well, let's see. If we've got 52 cards in the deck, right? So 52 cards. Let's see, we've got 13 hearts, 12 face cards, then 3 that are both face cards and hearts. So then we can say that we can take, so we have a probability of rolling 13, 52, so the probability of that event is going to be 13 over 52, that's the chance of getting a heart, plus 12 out of 52, that's the chance of getting a face card, minus 3 out of 52, that's the ones that are both. We don't want to double count them. And all of that becomes 11 out of 26. That's our probability of getting this particular configuration. Now we can say that if we wanted to get super fancy, which we actually normally don't want to do, but if we do want to add up all the probabilities from something that was like this, you had all these different overlapping things, you can do that. And the way to do it is you add the probabilities, the individual probabilities, and you subtract and add and subtract and add all the intersecting areas or probabilities. And that's how you can come up with a formula for this much more complicated situation, which we normally won't have to cover. So let's see now. Falling asleep feels easiest when? Da, 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 da. Hopefully not right now. And in any case, I wish you a very good day, evening, or whenever you have actually watched this video.